Hello everyone. Welcome back to the session on your Unit 4 Part 2. That is nothing but deadlocks. So in this particular session, we'll be continuing the previous session what we had discussed related to your deadlocks. In the previous session, we actually discussed about the introduction part of your deadlock. Exactly what do you mean by deadlock? A situation where we may not be able to come back. That situation is what we call it as a deadlock situation. And the similar kind of situations we can see in our practical world as well as in our operating system itself. So here in this particular topic, we are going to discuss about the different scenarios why this particular deadlock situation actually arises and how we can overcome that particular problem. Okay, using different algorithms or different strategies. That is what we are going to discuss in this particular session. So in the previous session, we discussed about something called as system model. Okay, just a minute. Okay. So in the previous session, we discussed about something called as system models, where we discussed what exactly the model of a particular deadlock actually looks like. And within this, we also discussed some brief introduction to something called as RAG. I think you people remember it. That is nothing but resource allocation graph. So we actually discussed about some of the terminologies and some of the methods how we are going to use in our coming sessions related to handling this particular deadlock. So that we are going to see in this particular. So in this, the first what we discussed about is something called as RAG. That is nothing but your resource allocation graph. Apart from that, we also discussed about the way how this particular deadlock arises and what exactly the important features are there within this particular thing. That is nothing but the necessary conditions for the necessary conditions for occurring a deadlock. I think if you remember the previous video what in which we have discussed it. So in the first and foremost what we have here is something what we call it as mutual exclusion. Okay. And next necessary condition we had is nothing but hold and wait. And after that we had something called as no preemption. And finally what we have here is nothing but circular wait, I guess. Right? Yeah. And we said that if all these four conditions are present in a particular scenario, okay, where the processes are exchanging the resources, in that particular scenario, if we have all these four conditions simultaneously, then definitely we can say that there is a deadlock situation and that particular scenario. So that is what we have discussed in the previous session. And apart from that, we also said that how we can represent this allocation of resources to a particular process and how these processes can request using a graph technique. We call it as resource allocation graph, where we discuss that every graph, it means we know that a graph generally consists of set of vertices and nodes, right? Vertices. And okay, fine, we call it as edges. Okay, vertices we call it as nodes, and here we call it as edges. And these vertices again we actually classified into two types, I guess, if I am not wrong. Vertices. So that is something for resources, and another one is something for process. And process we actually represent using a circle, and whereas resources we are going to represent with the rectangle. And within the resources, we said that one particular resource can have multiple instances. Multiple instances. So means that we are representing using dots. Means for example, this is your printer. So this printer has two instances of resource type printer. Okay, it is having two instances. Means what does that mean? Simultaneously, two processes can give order for printing. Okay, even the print will take place one after another, but simultaneously these two processes can give the instructions to this printer to print the data. Okay, so it can hold. If another process comes at the same time and is giving the instructions to print the data, well, this cannot be taken by this particular printer because it has a capacity or a limit of only taking two orders at a time. It can't take the third order. So if any one of the process completes execution, suppose P1 has completed, then the printer can take the third order. That is the order from P3. Apart from that, so that is what we call instances. So every resource will have certain instances, and based on that instances, we are going to allocate that particular resource to the particular process. And remember, those instances are represented using dots. Anyhow, we have completed this everything, whatever we are discussing here in the previous video. So if you want, you can just go through it. Okay. So in this session, what we are going to discuss, well, basically, the thing what we are going to discuss here is something like, characterization we have discussed. Today's session will actually trying to cover these three topics here. So what are the methods we have for handling deadlock? And then we are going to discuss about how we can prevent deadlock from occurring. Okay, so, and then we have something called recovery. So in case a deadlock situation arises, well, this is the last topic I am discussing here because this doesn't have any relevance with the previous algorithms, whatever we have. So that we'll see in the coming session. So I'm actually covering the last topic here itself along with this deadlock prevention. So if you talk about, so basically, without waiting, let's go ahead. So today we are going to discuss about the different ways how we can overcome this particular deadlock problem. Well, basically here, some people have given their opinions, okay, in a format of steps, and that we can follow it up. First thing is, we is saying that the first step how we can overcome this particular deadlock problem is ensuring that the system will never enter a deadlock state. Okay, so means we might be using some kind of protocols here, making sure that this situation never comes in the particular operating system. This situation never arises in the operating system. Okay, this is something like, we call it a precaution, taking precaution. Like, we know that during winter season, a lot of mosquitoes comes and there is a possibility of getting malaria and all. So we'll take the necessary precautions in order to overcome that. Okay, so we are taking some measures using which we are trying to overcome that particular problem. Means we'll never let that problem to enter into our world. So that's what he's talking about in this particular thing, ensuring that the system will never enter into a deadlock state. So what we can do in order to make sure that we never come across a deadlock state, so definitely we need to use some kind of protocol or program. We need to use some kind of program which can either prevent a deadlock from occurring or it can totally avoid that particular situation. So these are the two things. So we have two algorithms here based upon this scenario. One is what we call it as deadlock prevention. So today we are going to discuss this particular deadlock prevention, and another one is deadlock avoidance. Well, this one we will discuss in the coming session because in this we need to use some example and then we have to solve some problems how we can avoid a deadlock situation. So we do have an algorithm protocol for this deadlock avoidance. Using the protocol, we need to solve this particular problem. So that will be coming across here. Next, we have something called as deadlock prevention here. So this is what we are going to discuss in the today's topic. And the next step, what is saying here is that we can allow a system to enter into a deadlock state, detect and then recover. Well, basically, this is the third algorithm is talking about deadlock detection. So in this particular unit, this particular sub part, we are actually having three important algorithms here. The first one is deadlock prevention, deadlock avoidance, and deadlock detection. Well, basically for deadlock prevention, we don't have any kind of protocol here. Just he has given the assumption that if we can make sure this thing happens, then we can prevent a deadlock situation. That is what he means to say. And anyhow, we are going to discuss in the coming slides. In deadlock avoidance, what he's doing is, and in deadlock detection, he is providing you with different algorithms. Using that algorithm, you first, what he's saying is, okay, you try to avoid that situation. Never let that situation to come using that particular protocol. That is what he's saying here. The third one, deadlock detection, what he's saying, okay, anyhow, we have taken measures, still deadlock situation has come up. A deadlock has come up in our system. Something like, okay, someone has fell ill due to malaria. Now, what is the next step we need to do? Obviously, we need to go to the doctor, get the pills, and get it ready. Isn't it? We need to overcome that particular problem. We need to identify whether it is really a malaria or it's simply a viral fever. So if it's a viral fever, we'll take a small pill of it, okay, and we'll try to overcome that particular situation. If it is malaria, we'll take some situation. Same way here also, okay, anyhow, even though taking precautions and avoiding it, a deadlock has arisen in our operating system. So we will be using this algorithm to detect exactly where this particular situation has arisen in our operating system, and based on that we will take some necessary steps to overcome that particular problem. Okay, so that is the second step. And the third one is the one which is mostly used by all the operating systems, including your Linux and Windows. That is, ignore the problem and pretend that deadlock never occurred in the system. Means altogether they are simply pretend, okay, that this kind of situation will never occur in the system. The third one is the one which is used by most of the operating systems. Okay, whether you take it or something called as Windows or sorry, you can take it Windows or you can take it Linux flavor. Whatever the flavor you're taking, either Windows or Linux or any other operating system, all this uses the third point what we are discussing here, ignoring the problem and pretending that the deadlock never occur in the system. Now, because of this particular situation, now what happened here? It becomes the responsibility of a programmer. It becomes the responsibility of a programmer to make sure that whenever he is writing a program, it actually overcomes the deadlock situation, overcome or detects the deadlock situation. So indirectly, they have left to the programmers itself or the developers itself. So whenever you're writing a program, make sure that you people are not using or not writing a code in such a way that the deadlock situation can arise in the system. That is what exactly they have done using this particular thing. But mostly all the operating system pretend the third one. Okay. So let's see what are the different algorithms we do have. So in order to overcome that, first is deadlock prevention. Now, well, what exactly is saying in this particular scenario, he has just given a glimpse of it. So deadlock prevention, what is saying that we know that when a deadlock situation arises, right? When a deadlock will arise, we already discussed in the previous session that a deadlock may arise only when one of the four necessary conditions, when all the four necessary conditions takes places. What is that? Mutual exclusion, hold and wait, no preemption, and then finally, last but not the least, circular wait. If all these conditions are holding, then we are saying that a deadlock has arisen, isn't it? That's what we were saying exactly here. The deadlock situation has arisen. Now here, in deadlock prevention, he is saying that if we can make sure that at least one of these particular condition is not holding it up, then that particular situation is going to be overcome. That's what he's saying in this particular scenario. Hold on. Okay, I hope you people got it, what I mean to say here. So if we can make sure that at least one of the necessary conditions we can eliminate it. So if all these four conditions, if we can at least remove one of the conditions, maybe a mutual exclusion, hold and wait, or no preemption or this, automatically the deadlock situation will be overcome. That is what he's saying in this particular deadlock prevention. What about deadlock avoidance? What he means to say here in this particular thing? So here what he's saying is in this particular deadlock avoidance, there is some conditions here that the operating system should be given a prior information related to the resources that a particular process is going to use. Okay, a particular process is going to use what kind of resources throughout the lifetime. Means whenever this process is created and when it is going to finish, in between whatever the resources this particular process is going to use, all that information should be given in advance to this particular operating system. And when this particular process will request for that particular resource, the operating system will decide whether that can be allocated to that process or not. Okay, if we allocating that process that particular resource and there is no deadlock situation, then the operating system will give that resource to the process. In case when he is requesting that particular resource and there might be a deadlock situation, then the operating system will not give the resource to that particular process. Rather, this process has to wait until this particular resource is available and no deadlock situation is coming. That is what actually happening in your deadlock avoidance. Okay, deadlock avoidance, what is going to do exactly here is whatever the processes are we are going to generate, any process that is getting generated, it should give the prior information regarding all the resources which this particular process is going to use throughout its lifetime, right from when this process is created, right when it is going to end. In between, it might be using many resources, right? Resource 1, 2, 3, 4, these resources. So all this information, whenever it is entering, okay, it has to provide the information related to these resources to this particular operating system. And whenever it will require, now all these resources will not be requested by this process at a time. Okay, he is simply giving the information. In the future, I may be using these resources, but whenever time comes, he will request that resource from the operating system. That is what he's saying. But that is based on that, what happens whenever that situation comes, he wants another resource, something like R3. This resource he wants to use after some time. So he will request that to the operating system. Now operating system has a table. It will maintain a table related to which resource is allocated, which resource is available, and based on that it will decide whether this particular request, whatever is coming from this process, can be granted or not. If a request means if that request is granted and a deadlock situation is coming, then the operating system will not give that resource. Rather, it will and make this process to enter into a wait state until that particular resource instances are available. Then that particular instance will be provided to this process and the deadlock situation will not arise. So this is the way how exactly this particular deadlock avoidance situation takes place. Well, we can explain them more briefly and more nicely using an example that we'll see in the next session. So today's session is mostly we are going to focus on deadlock prevention. And I already told you what is the solution for the deadlock prevention here is making sure that at least one of the four conditions, at least one of the conditions is not holding back. Okay, so what are the four conditions we have? Mutual exclusion, hold and wait, no preemption, and circular. So among these four conditions, at least one of the conditions we can stop. Any one of the conditions we are able to stop, then the deadlock situation will not come. That is what he means to say in this particular scenario. Okay, let's directly dive into it. Deadlock prevention. Let's see one by one how we can give solutions to each and every solution. Like I told you that we can hold at least four. So if you talk about mutual exclusion, how we can prevent mutual exclusion. Okay, so how we can provide a solution in order to avoid this hold and wait condition. How we can try to avoid a situation related to something called as no preemption and circular weight that we are going to see in this particular thing. The first and foremost thing is mutual exclusion. What do you mean by mutual exclusion here? Basically, we know that when one process has access to a particular resource, no other process should try to use this particular resource until this particular process is releasing this resource on its own. That is what he's saying in this particular thing. That is the definition of your mutual exclusion. So one process or resource, one resource can be used by only one process at a time. And when it is using, no other process should be given the permission to hold it. That is what he's saying here. Now, in this particular scenario, basically, if you talk about resources here, we know that resources are basically classified into two types. Okay, something we can call it as shareable. Some resources are non-shareable. Yes. For example, okay, let me give an example so that you can understand. Okay, I have a file. Let us suppose I have gave you unit for notes. Okay, I have provided you a unit for notes. I have shared it using a Google Drive to all the 54 or 55 or some 56 or 60 students. So when I am sharing this particular file, I am setting the what we call rights. Okay, and the right is that you people can open this file only view only mode. What does that mean? All the 60 students or 70 or 80 students, they can try to open this file only for reading purpose. They cannot do any kind of modifications to the file which I have given to you. Okay, so can all can open at the same time and read it? Yes, it's possible because there are no modifications are going to be performed on that particular file whichever has been shared here. Okay, so in that way, what he's saying is we can first differentiate between the resources that are non-shareable and shareable. So if we talk about shareable here, that resources will remove it from this particular criteria of mutual exclusion because that will not come under that mutual exclusion. Where mutual exclusion is required, whenever some kind of modifications can be done on that particular file or that particular resource, then we require something called as mutual exclusion. So only for those resources we are going to apply this mutual exclusion concept. Whereas coming to the other resources, we are not going to apply this mutual exclusion concept. That is what he's saying. So here non-shareable is nothing but in the previous part 1 we discussed about mutex lock. I don't know how many of you remember. If you don't remember, please watch my previous video so that you can get a clarity. So here mutex lock we have used. So whenever a process want to enter into a critical section, it will first request. Once he is getting a permission to enter into it, he will be calling a mutex lock. Using semaphores we have discussed. Okay, so it will enter into it, it will simply lock it up so that no other process can try to access this critical section. So once it's coming out, then this particular, he will give a signal to every other process, they can request and they can enter into the critical section. This is the whole process actually takes place. So here that kind of scenario, so that kind of resource. Now mutex lock is a resource. Semaphore is a resource, right? Now these cannot be accessed directly by each and every person or each and every process. So that's why we call them as non-shareable resource. And for this, we are going to apply this mutual exclusion condition. So this is one of the way how we can try to avoid mutual exclusion. But we can try to avoid mutual exclusion only for shareable resources. Non-shareable means definitely you require mutual exclusion condition. Okay, the very next thing what we have is hold and wait. Okay, let's discuss about the definition. What do you mean the hold and wait? In that we discussed that whenever one particular process, okay, whenever one particular, okay, let me draw the diagram and show you. Whenever a particular process want to access a particular resource, let us suppose R2, he should have at least one resource in hand. Then only he can request another resource. That is what hold and wait. Means whenever a particular process wanted to access a new resource, he should hold at least one resource in prior and then only he can access it or request for the another resource. If he is not having, then he cannot access the next resource. That is what we have discussed. So how we can overcome this problem? How we can overcome that definition? Simply one thing what we need to do here is we need to go in the opposite direction. If he's saying you to do this thing, you need to go in the opposite direction. So what he's saying, whenever the process is requesting a resource, then he should have at least one resource with it. We'll go in the opposite direction. So in opposite direction, when you are implementing it, we have two protocols here. Two protocols are coming handy for this particular hold and wait. So you can apply this in order to overcome this hold and wait condition. So what is the first protocol here is that every process, okay, we know that whenever a new task has to be implemented, the operating system creates a new process. And this process, what it is going to do is, it will give information, it will give all the resources what it wants. The first protocol, what is saying is, this particular process, whenever it's initiated, whatever the resources this particular process requires, it will request in the beginning itself. In the beginning itself, it is going to request all the resources. And we will be allocating all those resources to this particular process. We in the sense the operating system. In the beginning itself, it will give it all the resources to this particular process. And then it will perform the operation. Okay, it's not like now it will hold one, means it will initially request one resource and then it will wait. Now whenever it requires another one, then it will request, no, not like that. In the beginning itself, it has to tell, okay, I want these resources, and all these resources should be given in prior to this particular process. That's what happened here. That is the first protocol. What about the second protocol we have here is that, okay, in this case, we are going to little bit change it up. The process will request resource only when it has none. Means, in the sense, the process will request some resources in the beginning. It will start working with it. It will start performing operations with it. Once it has completed and it wants another resource to complete the task, then it has to release the previous resources what it is holding. Okay, and once it is holding, and then these resources along with the other one should be provided to it, new one, it should be provided to it. Then only it can perform the operation, or else it is not going to perform the operation. That's what he's saying in this particular scenario. I hope it's very clear. The first protocol, what it's saying is, whenever the process is created, it will initially request all the resources what it wants. It will give the list. I want these resources, and all those resources we are going to allocate to that particular process. The operating system will provide it, and then it will start performing the operation. The second method, what it's saying is, the process, what it is going to do is, it will request a resource, some resources, not all. Suppose it requires 4 resources. For example, if a particular process requires 4 resources to complete a task. To complete a task, it requires 4 resources. But in the beginning, this process will be requesting only 2 resources, because in the beginning it requires only 2 resources. So it will start performing operation with the help of 2 resources. And once this is completed, now it requires third and fourth resource. So before it can request this 3 and 4, it has to release 1 and 2. Whatever the task it has done, it has to release this particular resource, and then it has to request 3 and 4 so that it can perform the operation. That is what he is saying. That is the meaning of your first one. Allow a process to request resource only when it has done. So first initially it has no resource. It has requested 1 and 2, perform the operation. Now it requests 3 and 4 to perform the operation. So what it will do, it will release 1 and 2. So he is not having any resources now. Now he is requesting 3 or 4. Now the operating system will allocate it. It will perform operation using 3 and 4 and complete the task. This is the whole thing. Now this same thing I'll explain with the help of a small example, because we do have some drawbacks and then some differences between this first protocol and the second protocol. Okay, so protocol 1, and here we do have protocol 2. Okay, let me take an example. That we are going to take one scenario or one situation here, that you people are going to copy our data. You people are going to copy a data from a DVD, okay, into your disk drive. Okay, disk drive is nothing but your internal. Your laptop having a secondary storage device. Now that is what I'm talking about. Disk drive. Already we have discussed it. So disk drive. So what we are doing, we are going to copy the data from a DVD into a disk drive and store that information. Store that information in your disk drive, and we'll apply a sorting algorithm, any sorting algorithm on it, and finally we will print that data using a printer. Please understand the scenario here. We are going to copy a data from the DVD. Okay, we are simply going to copy a data from the DVD into your disk drive, and in the disk drive we will be placing it and we will sort in a order, alphabetical order, maybe ascending or descending, and then finally we'll print the data using a printer. Now what are the resources we require here? What resources we exactly require here? Can anyone tell me? Resource 1, resource 2, anyone? Okay, fine, I'll explain it. So resource 1, we can say something called as this. The first resource what we require is DVD, because from the DVD only we can collect the data. That is the first resource. Then what we require here, DVD, means we need to store that data from the DVD into your disk drive. So we require a disk drive. That is another resource. And third one is the printer, because we are applying some sorting technique in the disk drive. We are sorting it up and then finally we are printing it up. Fine. Till here, it's okay. Now let's see the first protocol, how we are going to implement. Now in the first protocol, what did we discuss? The first protocol says that whenever a process, so we have created a process P1. This is the one which will perform this operation. It will try to get the data from the disk drive, store it into your, from the DVD, store it into a disk drive, apply a sorting algorithm, and finally print it. This is the responsibility of this particular process. Now, in the protocol 1, we discussed that this process will request all the resources in the beginning itself whenever it is created. Means this particular process P1 will say to the operating system, I want a DVD, I want a disk drive, and I want a printer. Now what we will do, the operating system will allocate all the 3 resources at a time in the beginning itself, and this particular process will start performing. But the problem here is that resource utilization is not perfect. The main drawback of this is the resource utilization is not perfect. Can anyone tell me why? So if you look at this particular scenario P1, well, does this particular process have any work with the printer till the end? Means the whole process from here to here, until this whole process is completed, this particular process will not have any work with the printer, because it has to copy a data from the DVD into a disk drive, then apply the algorithm, sort it up, then it requires the print. So in between it will take some time to perform this operation, right? In order to perform this operation, it will take some amount of time, and during that time this printer is sitting in an idle state. And this printer cannot be used by another process. Why? We have already allocated to this, and until he is releasing this printer, no one else can use it. But he is not going to use it. Let us suppose it will take 5 minutes to print a document. So let us suppose 4 minutes it is taking to perform the operation, like copying the data from the DVD, sorry, storing the information into the disk drive, and then sorting it up. So in order to perform the whole scenario there, it will take 4 minutes. And the last 1 minute, the printer is required to print. Means the previous 4 minutes, this printer is sitting in an idle state. So we are not utilizing the resource perfectly using this particular protocol. That's the problem with this particular protocol 1. Now come to the next protocol, the second protocol what we have discussed here. So in this, what did we say? The process will initially request some resource. Let us suppose P1, he has initially requested DVD and disk drive because he has to get the data from the DVD and store it into the disk drive. So what the P1 will do, it will request only these two resources and we have allocated it. So here DVD is given and from here the data is copied into the disk drive and then it's performing some sorting algorithm. Fine, done. Now what he requires? Printer. He requires printer. But before requiring a printer, what did we say? It has to release these resources. So P1 will release these two resources and again freshly it will request another two resources. That is nothing but your disk drive and printer. And now since we have a data in a sorted order here in disk drive, that data will be printed using a printer. This is the whole. But here also we do have one drawback. What is the drawback? You see, it is getting the data from the DVD and storing into the disk drive, applying some sorting algorithm and sorting the data. Now, after sorting the data, it is simply releasing these two resources. So there is no guarantee that the next time when so it is requesting the disk drive and printer, that data which he has already sorted and placed in the disk drive is available in this particular drive. There is no guarantee. We can't guarantee. If it is available, well and good. This protocol is good. But in this case, but in another scenario, in another alternative way, if we think here, if it is requesting again after releasing a disk drive, there might be a possibility that that particular disk drive may not have the data which he has sorted. Now what will happen? Then we will not be able to print that particular data. So these are the some problems that are existing using this protocol, but still we are using it. Protocol 2, we are just going with the assumption that disk drive will definitely have that information stored. You people are creating a file, you save it up. When you close it and you open it, you get that particular file in the same drive wherever you're storing it. So that is what we are expecting and waiting. So the main drawback what we have is resource utilization is not perfect, and another one is starvation. Another problem here we are facing here is something called as starvation. How we are starving here? Well, basically, if you talk about your starvation, what I can say is, see, if this particular resources, if a particular process requires high-end resources, high-end or high priority resources. Okay, if a particular process requires high-end or high priority resources, there is a possibility that this particular process may not get all the resources at a time. Because high priority resources mean definitely it will be used by multiple processes and every process may be having its own priority. In that case, this particular priority may not be able to get all the resources what are required and it may not be able to perform a task. So that is what we call it as starvation. That's what we call it a deadlock also, I guess. Okay. So starvation. So there are two problems that associates with hold and wait protocols what we are implementing here. So that is resource utilization is not perfect in this case and second starvation. Okay. I hope it's very clear with the help of this hold and wait condition. So the first protocol what we are going to do? What is the first thing we did here? What is the first thing we are exactly going to do here is in the protocol 1 I already told you protocol 1 sorry protocol 1 what we are going to do all resources required all resources which are required by a process are allocated to it. When we are allocating in the beginning itself, before it starts doing the work, in the beginning. Protocol 2, so the process will request some resources, not all, some resource and perform the operation. And it will perform the operation. When it needs a new resource, it must release the previous one, previous resources. So these are the two protocols what we do have with respect to your hold and wait. So that's what we are actually going to see. We are seeing in this. Okay. The next point what we have is no preemption here. Now let's see how we can avoid this no preemption condition. So what do you mean by no preemption here? That whenever a process is allocated a resource, only that process is having the capability to release that resource. Until and unless until then, no other process can try to access that particular resource. Now that problem we have to overcome. How we can overcome? So here also basically we are going to use two protocols. Here also we are going to use two protocols here. The points what you are seeing here, these are related to your protocol 1. What is that? Whenever a process is actually having some resource and it is requesting some new resource which cannot be immediately allocated to it, then what we are going to do is whatever the resource that particular process is holding, we will release it. For example, we have a process P1. He is requesting R2, but this R2 is present with P2. And this P1 is holding, this P1 is holding R1. So what is this protocol is saying is, whenever this particular process is going to request another resource, if this resource is available, we'll allocate it. In case this resource is not available and it is held by another process, then what we will do, anyhow this process is not going to get this resource and is not going to use this resource because he has completed using this particular resource. We will simply remove this particular resource from this particular process and give it to someone some other process which is requesting this particular resource. Okay, and the process, whatever the resource we have printed here, that will be adding into the list of resource for which the process is waiting. So P1 is actually waiting for R2. Okay, so in the meantime, what we did, we removed R1 resource from the P1, allocated to P3. Now this particular process within the list, he is requesting R2, it will be given R1 also. It will request now R1 also. So once this process completes, it will release the resource. Then if this process is also completing and is releasing the resource, then both the resources will be given simultaneously to this particular process to perform the operation. Okay, that's what the first protocol we actually going to discuss here. Let me explain it one more time. We have a process P1. He is requesting a resource R2 and this resource is present with P2. Okay, and we have another resource here R1 and this resource is present with P1. And here we have P3, another process, and he is requesting R. Now what he's saying is now this process is actually completed using this particular resource. He wants this resource to complete the task. He did whatever the work has to be done. But this resource is held by whom? P2. So P2 is not going to release it. So definitely P1 is not going to get this resource. So but in the meantime, he is not utilizing R1. So the operating system, what it will do, it has observed that R3 is requesting R1. So he will simply remove this resource R1 from P1 and it will allocate to P3. So P3 will perform the operation. In the meantime, P1 is requesting, he is having a list. He has requested R2. In the list, there will be R1 also. We'll add it into it. So once P3 has completed in the meantime, and in the same time, P2 has also completed. So both of them are going to release the resource, R1 and R2. And this process requires both the resource. Now R1 and R2 will be allocated to this particular process and it will start performing the operation. Once it's completed, it will release R1 and R2. So this is what he is talking about in this particular scenario. Just go through the thing what we are doing here. If a process is, let's go through the statement what is saying. If a process that is holding some resource request another resource that cannot be granted immediately, then all the resources currently being held are released. So that process which is requesting P1 was requesting. So whatever the resource he is holding, we will simply release it. Sorry. Now the preempted resource means we have simply preempted it. What is the condition here? No preemption. No preemption should be done. But what we are doing, preempting it up. That is a protocol. So we are preempting it means we are removing that particular condition. So if we are removing that particular condition means there will not be any kind of deadlock. That is what we are doing exactly here. So preempted resources will be added to the list of resources for which the process is waiting. So P1 is waiting for R2. Along with that, we will add it R1 also. So once the process will be restarted only when it regains its old resources as well as the new one. So what is the old resource it is requesting? R1. What is the new one? If both are available and given to it, then only it can start performing its operation. That is the first protocol. Then what about the second one? Second one is also similar to it, but small variation. What is the variation here is, whenever a process requests some resource, the system first checks whether they are available or not. Common thing. P1 is there. He is holding R1. Okay. And he is requesting R2. So first operating system will see if it is available, it will be allocated to P1. If it is not available, then we will check whether they are allocated to some other process or not. Means let us assume that P2 is there. P2 is having this resource. That is what. So operating system is checking whether this resource is present in some resource or not. Yes, P2. With P2 it is available. Now, and now what we are doing, allocated to the some other process that is waiting for additional. Now let us suppose this P2 is waiting for R3. Okay, I'm just taking a small example for your understanding. That's it. Okay, you can take any kind of example and you can explain it. So P2 is requesting for R3. Okay, so what happens? This is also in a waiting state. Okay, so P2, what is saying? P1 has requested R2. So R2 is not available. Now we will see whether R2 is used by which process? P2. Is he available or not? Means he using that process or he is waiting for some other process. Now P2 is waiting for some other process. We'll simply preempt this process and we will allocate this process to that particular process P1. I hope you got it. Okay, you're getting my point. Take another scenario. Suppose we have a P1 here, resource 1, resource 2, P2. So resource 1 is with P1, resource 2 is requesting this, and he is. Now in this scenario, let's see both the difference. What is the difference? We don't have R3 now. Now P1 has requested R2, but R2 is with P2. Okay. Now we will see, the operating system will see whether P2 is requesting for some other resource or not. Right now, based upon this diagram, P2 is not requesting. He is only using resource R2 and start working. In that case, this particular process has to wait. We don't have an alternative. But in this scenario, the process P2 is waiting for some other resource R3, which is held by some other process P3. Now in that case, what happens? We can simply, the operating system simply will preempt this resource R2 and will, because it will take some time to get this resource R3, isn't it? So in the meantime, why we should keep this resource idle? It will simply preempt and it will give this resource to P1. P1 will start working on this, perform a task with R1 and R2, complete and just move out from there. Then this resource will be again allocated to P2. And in the meantime, R3 will be available and that will be allocated. So these are the two scenarios that are going to implement using this protocol. So these are the second protocol what we have. Understand it very carefully here. Okay, what is saying? Whenever a process requests some new resource, if the system first checks whether they are available. If it is available, allocate it. If it is not available, we will check whether that are allocated. Means that particular resource which has been requested is allocated to some other process or not. And whether that process is waiting for additional resource or not. Okay, so we are saying whether the process is waiting for some other resource or not. And if it is, then we'll simply preempt the desired resource from the waiting process. So P2 is waiting for R3, we'll simply preempt R2 resource from P2 and we will allocate to this particular P1. If the resource is neither available, not held by the waiting process, that this scenario is talking. The requesting process must wait. While it is waiting, some of the resources must be preempted, but only if another process requests them. So C is describing this particular scenario. So R2 is actually held by P2 and he is not waiting for some other resource. So then in that case, what happens? We can simply preempt, we can't preempt this resource. So this process should enter into waiting state. But we can preempt R1. If some other process is requesting this, we can do that. So using any one of the protocol, we can overcome this particular chain. Okay, remember what we are exactly doing here. Please don't get diverted from your main goal. What is the goal here? We have 4 steps. What is that? Mutual exclusion, hold and wait, no preemption, and finally circular wait. What is saying? If all the 4 conditions exist, a deadlock will come, right? We are making sure at least one of the conditions is not getting holded. So if there is a scenario that no preemption can take place using this protocol, we'll implement it. So that this particular condition will not take place. So even though these 3 conditions are taking place in a scenario, this condition is not taking place, so there will be no deadlock. So hold and wait, we use the 2 algorithms. So if you at least apply one of the algorithm is implicable, okay, applicable in that particular scenario, we can overcome this particular deadlock situation. That's what it's saying. And the last but not the least, circular weight. So let's see how we can overcome the circular weight. So what do you mean by circular weight here? So we have set a process okay, I'll take with P1, P2, P3, P4, Pn. We have resources R1, R2, R3, R4, Rn. So every process is holding one resource. So on up to this. Now what is circular weight? Now P1 requests R1, P2 is requesting R3, P3 is requesting R4, P4 requesting R5, so on up to Rn. So and Pn is requesting R1. So this is what we call it as circular weight. So how we can overcome this problem here? Here simply given a solution is we can give a order to all the resources. Whatever the resources we have R1, R2, so on up to Rn, every resource we will give some value, a natural number. Every resource will give some value, a natural number. That is what it's saying here. Okay, and how we will give is based upon the priority. If you look at here, the tape driver is having a least priority, so we gave the number 1. This drive is having much more higher priority than tape drivers, we gave it as 5. What about printer? Almost everyone uses it, so we are given a tape drive, means the number, the natural number what we gave for the printer is 12. Now based upon this, we are actually describing two protocols, and if you are using these two protocols, any one of the protocol you are implementing it, then this deadlock will not take place in the situation. So what is the first one here? If we talk about first protocol, what it says is that whenever particular process requests a resource, it should request in an increasing order only. For example, a particular process is there. I said that it wants to, okay, let's take a previous example. A process need to read a data from the DVD drive, that is nothing but your tape drive. Store the data into your disk drive, and then it can order, it has to print that data, sort it and print that data. Now it can, now this particular resource, I mean this particular process can request them in increasing order. Means in the beginning itself, the process P1 cannot request printer. Okay, in the beginning it can print, okay, because it is not having any resource, it is requesting printer first, we can give it. But after giving the printer, if it is requesting disk drive or DVD drive or DVD tape, we cannot allocate it. Why? Because this particular printer is having higher priority. So he has requested higher priority. So next time whenever he is requesting another resource, the priority of that particular process should be greater than whatever the resource he is holding it. That's what the condition. F of Rj should be greater than Ri. So Ri is first resource. Let's take R1 and then another resource. So whenever a particular process is requesting the next resource, the priority of that resource should be higher than the priority of low resource, whatever it is requesting. Okay. Okay. Let me explain it now so that you can get a small clarity if you are confused here. So P1 he's requested printer in the beginning. Initially he don't have any resource, he has requested printer, priorities 2, you gave it. Next time he is asking you disk drive, second time, means after using that resource he is requesting disk drive. What is the priority of 5? Now the system will check whether which one is greater. 5 is greater than 12 because this is the next resource now. Second resource is greater than first one, but here the condition fails. Why? Because the second resource, whatever the process has requested, is having a priority 5, which is less than the priority of the first one. But what is the condition we give here? Whenever the process requests a new process, its priority should be higher than the next previous one, whatever he has requested. So this condition fails here. So what is the order it can request? So first the process should request tape drive. What is the priority 1? Next, the process can request disk drive, priority is 5. So 5 is greater than 1, condition satisfied. So we can allocate disk drive to the process. And after some time, this process is requesting printer. So printer, what is the value? 12. So 12 is greater than the previous one. Previous one is 5. Greater than 5, condition satisfied. So we can allocate a printer to this particular process and perform the operation. In this way, it can do it. Or else it can't do it. We will not be allocating. Means whenever a process is requesting, it can request any resource in the beginning. But the next time whenever it is requesting, the priority of that process, I mean resource, should be higher than the previous one which has been requested. Simple logic. And after that, the second protocol, what is saying here? In the second protocol, what he's saying here is, well, same thing, but only thing what there is an alternative here that whenever, suppose in the beginning we said that process has requested printer first, 12, and after that he is requesting disk drive. So priority is less. So we cannot allocate this resource to this particular process. That's what we are saying, right? P1. Because initially it's requested higher priority process, now it's requesting low priority. So it's not possible. Descending order is not possible. Ascending order is possible. So what we are saying in the second protocol is, okay, in case this process requires urgently this one, then he has to release this particular resource. Yeah, he has to release this particular resource. So once he is releasing the resource, P1 will not have any resource. So definitely he can request any kind of resource. So immediately it can have it. So whenever a particular processor requested a high priority process first, then that particular process is requesting a low priority when compared to the first one. Then it has to release this particular resource, and then only this low priority resource can be allocated to that particular process. That's what we are doing here in this particular scenario. So these are the two protocols. If you are implementing any one of it, automatically the chain will remove. Means what are the four things we have? No mutual exclusion, hold and wait, no preemption, and circular wait. One of the conditions will be eliminated. So definitely deadlock will not take place. It's very, very easy. So that is all about for your deadlock prevention method. So that is what the whole scenario we are going to do it. And now we have a small topic here, something called as recovery from deadlock, how we can actually recover it. So what is saying here is, in case whenever a deadlock detection algorithm, well, okay, we did not discuss this deadlock detection algorithm. Okay, we will discuss that in the next session. Okay, it's a big topic, and we need to solve some practical examples related to it. That's the reason we are not discussed it. In the coming session, we'll discuss it. Anyhow, okay, we'll do one thing. Once we complete that and deadlock avoidance, then we'll discuss about deadlock recovery. Okay, so this is all related to your deadlock recovery here. So with this, we complete this particular topic, and the next session we'll try to cover your deadlock avoidance and deadlock detection. And after completing that, we'll go ahead with the deadlock recovery. It's very easy. But before you understand deadlock avoidance and detection, that's better, because deadlock detection will be implemented here in deadlock recovery. So I just want you people to understand that, and then we'll go for this particular thing. Okay. Thank you. Thank you for watching.